Hi everyone. I'm going to be talking about the main theorem of Galois theory today. Okay, so here's the setup. We're going to have F, a field, F inside the extension, field, and let's say it's finite. Now we're also going to assume F K are characteristic 0, just so we can use all that theory we've developed. Okay, so here is roughly speaking the idea. Suppose F inside K is Galois. And remember, Galois means that K is the splitting field of some polynomial, or equivalently, or the size of the automorphism group, K over F, is equal to the size to the index of K over F, or if G is the group aught K over F, then the fixed field by G is actually equal to F. Alright, so remember that's our setup. Okay, now here's the fun thing. Let's suppose we have F inside L inside K. Okay, now any automorphism of K that fixes L, so this is just a map from K to itself, which sends every element of L exactly to itself, is certainly an automorphism of K that also fixes F. Because if I fix everything in L, I definitely fix everything in F because L is bigger than F. Okay, so suppose we have this containment. This is a subgroup. Okay, let's give them names. Let's call this one H. It's going to be a subgroup of G. We already called that one G. Now, K sub A, or the subfield of K which fixes the subfield of K which is fixed by H, that's going to be L. And the reason this is because L inside K is also Galois. Remember, if K containing F is the splitting field of maybe f of x in f of x, then since f of x is also in L of x, K is the splitting field of f of x over L too. Okay? So L over K is also Galois. Well, that means if H is the automorphisms of K which fix L, and that's what we did, then KH is going to be L. Because that's what happens when this is Galois. So L and K is also Galois. Okay, so what did we just do? Well, if I had a field extension between L and K, right, I could get H a subgroup of G, which is aught K over F. Okay? And from H, I can also get KH, which is a subset, which we just showed was exactly equal to L. Okay. On the other hand, if maybe A, a subset of G, and this is still ought K over F, is any subgroup of G, we can form K sub A. This is going to be a subfield of K, right? And since A is in ought KF, everything in A fixes F, so F is also in KA. All right. Now, since K over F is Galois, just as above, K over KA is also Galois. Okay. Now, I can look at ought K over KA, right? That's a subgroup of G, which is ought K over F. And when we think about this, I want to think about how A compares to this automorphism group. Well, A certainly fixes everything that's fixed by A. This is all the stuff that's fixed by A. So A is in here. All right. Now remember, the size of A is equal to, and this is just always true, the index of K over KA. And because K over KA is Galois, right, this is also equal to the size of ought K over KA. Okay, so A is actually equal to ought K over KA. All right, so what did we do here? We took A and G. From A, we got KA. That's a subset of K, subfield of K. And from KA, we get ought K over KA. Okay. And we just showed that was equal to A. All right, so we've done two things. If I give you L inside K, we get this H. And from H, we can get back L. And on the other hand, just given a subgroup, we can form the fixed field and then recover the subgroup again. All right, so what does this say? We have just shown the following theorem. And this is really the main theorem of Galois theory. Theorem. There is a bijection again between intermediate fields L K inside L, I'm sorry, F inside L inside K, and this is in bijection with subgroups of ought K over F. Now this whole thing, this whole bijection works if K over F is a finite Galois extension. Okay? And remember, how does this work? If I take an intermediate field, how does this bijection go? And proof, L is going to be sent to ought K over L. And a subgroup of ought KF, that gets sent to KA. Okay? And these are just the two things in the bijection, and they're inverses to each other, as we've just checked. That's what all our work above here was doing. Okay. Now, there's something that's pretty easy to check, and I just want to point it out, but let me just point out this one other fact. Okay. If A1 is a subset of A2, which is a subset of ought K over F, then okay, how do we compare KA1 and KA2? Well, if I'm fixed by everything in A1, that doesn't imply I'm fixed by everything in A2, because there's more stuff in A2. But if I'm fixed by everything in A2, then I'm definitely also fixed by everything in A1. So we get this. Okay? And if we have F inside L1, inside L2, inside K, these are field extensions, then ought K over L2, well, if I fix everything in L2, then I also fix everything in L1. Okay, so the bijections of the main theorem of Galois theory are containment reversing. Remember, if A1 is bigger than, if A2 is bigger than A1, that means KA1 is, if A1 is smaller than A2, then KA1 is bigger than KA2. And if L1 is smaller than L2, then ought K over L2 is smaller than ought K over L1. So all the sort of containments get reversed. Okay. My goal now is to just give you a quick example. This is slightly different than the one in the book, but let's figure it out. Okay. Let's let F equal Q. Okay. We're going to let K, how about we start with Q, join, I think we've studied before, square root of 2, square root of 3. We join these two roots. Now remember, K is the splitting field of x squared minus 2 times x squared minus 3. So K over F is Galois. All right, let's figure out what we can about this Galois group. Okay, so how about we start by identifying let's identify the intermediate subfields. Okay, and then we're going to also spend some time looking at the group. I think this group might actually be on your homework. I just did something really weird here. All right, well, just going to get rid of that, I guess. Okay. So K over F is Galois. Okay, so what kind of subfields can we find, or intermediate fields? We could make one L1, and we could just do Q adjoin the square root of 2. That's definitely between K and F. And of course, we can also do Q adjoin the square root of 3. Okay? And finally, there's one more that's maybe slightly less obvious. Q adjoin the square root of 6. That one's in there too. That's also a subfield. Okay, each one of these, all of these are degree 2 over Q. Just because the minimal polynomial in each case is a quadratic. Okay? Whereas K over Q, or Q is F, K over F is degree 4. All right. So, what we know is that ought K over F, this is a group of order, because it's Galois, this is a group of order index K over F. This is one of our equivalence conditions of Galois. Okay, this is a group of order K over F. Well, and order of K over F is 4. So, ought K over F is a group of order 4. Now, I don't know if you've done this in last semester or not, but there are 2 groups of order 4. One is Z mod 4Z. The other is Z mod 2Z cross Z mod 2Z. One is cyclic. This one's cyclic. And the other is not. And I think you've probably seen this all last semester, I'm going to assume. Use a lighter pen there. Okay. One cyclic, the other is not cyclic. Okay, now, the cyclic group has one proper non-trivial subgroup. There are 2 groups of order 4 up to isomorphism. Subgroup, and that's 0 to, that's just 0, 2. As a subset of 0, 1, 2, 3. The cyclic group has only one proper subgroup, 0, 2, non-trivial subgroup, the subgroup of there. But Z mod 2Z cross Z mod 2Z has 3 such subgroups. And if I just list them out, they are, okay, remember, elements in here are listed by tuples. The identity element and 1, 0, that's one subgroup. The identity element and 0, 1, that's another subgroup. And the third one is the identity element and 1, 1. That's a fourth, sorry, these are 3 subgroups, 1, 2, and 3, subgroups of Z2 cross Z2. All right. Now, since there is a bijection between fields, or between subfields, fields L, and we have F inside L inside K. Remember, this is Q adjoin square root 2, square root 3. This is Q. And subgroups of ought K over F, that's what our main theorem of Galois theory says. This forces, absolutely forces, ought K over F to be isomorphic to Z mod 2 cross Z mod 2. Okay? There's only two subgroups of order 4 up to isomorphism. One of them has one subgroup. The other has three interesting subgroups. This is the one that has three. And in our case, our subgroups of ought K over F are, okay, they are ought K over L1 Q adjoin square root of 2, ought K over Q adjoin square root of 3, that's L2, and ought K over Q adjoin square root of 6. And that's L3. Okay, so we figured out what the group is. We found these three subgroups. Why don't we take a little bit of time just to analyze this ought K over F group and see what else we can see. Let's try to see this really explicitly. Okay, so here's the idea. Ought K over F, or K over, remember this is just Q adjoin square root of 2 over square root of 3, some sigma in here, that's Q, is determined by where it sends square root of 2 and square root of 3. Square root of 2 can be sent to plus or minus square root of 2. Square root of 3 can be sent to plus or minus square root of 3. Because square root of 2 has to get sent to a root of x squared minus 2. Square root of 3 has to get sent to a root of x squared minus 3. So any element is totally determined by where it sends these. There are four possibilities. They all show up because the size of ought K over F is the size of K over F, which is 4. Okay, so we found these four automorphisms. Let's see which one of them fixes which subfield. Okay? Or these... Okay. So I'm going to write down these four automorphisms. We're going to have sigma 1. We're going to have sigma 2. Let me give myself a little room. We're going to have sigma 3. And I guess I will just... sigma 4 is kind of boring. That's just the identity. We need to worry about that too much. So let's say sigma 1 sends square root of 2 to negative square root of 2. And it sends square root of 3 just to itself. And why don't we say sigma 2 sends square root of 2 to itself, and square root of 3 to negative square root of 3. And finally, let's say sigma 3 sends square root of 2 to negative square root of 2, and square root of 3 to negative square root of 3. Okay? All right. And this one just sends everything to itself, because it's the identity. That's what the identity does. Okay. All right. So, the subgroups of G are ID comma sigma 1, ID comma sigma 2, and ID comma sigma 3. And so let's figure out the fixed field of each. I'll call this one H1, we'll call this one H2, and we'll call this one H3. Okay? We better get exactly one of these subgroups. And of course, the one generated by sigma 4 is just, I mean, everything is fixed by the identity, so that's not so interesting. Okay. Or these are the interesting subgroups that are interesting. All right. So let's consider k.h1. So this is q, adjoin square root of 2, square root of 3, and then we're thinking about what's fixed by h1. So this is equal to the set of all, how about alpha in k, such that, well, identity times alpha equals, or identity of alpha equals alpha, well, that always happens, that's sort of stupid, and sigma 1 of alpha equals alpha. That one's more meaningful. Okay. So, what elements of Q are fixed by sigma 1? Well, any element of Q, alpha in, I'm sorry, not of Q, of K are fixed by sigma 1. So alpha could be, it's going to be some kind of T1 times 1 plus T2 times square root of 2 plus T3 times square root of 3 plus T4 times square root of 6. And of course, square root of 6 is square root of 2 times square root of 3. And if this, and let's just compute sigma 1 of alpha equals, well, that's just going to be T1 plus, well, negative T2 square root of 2 plus T3 square root of 3, because sigma 1 just sends square root of 3 to itself. And then we're going to get a negative T4 square root of 6. Because square root of 6 is square root of 2 times square root of 3, so square root of 2 got sent to negative square root of 2, square root of 3 got sent to positive square root of 3, positive times negative is negative. Okay, and so if this equals alpha, then T2, T4 are 0, so alpha is in Q adjoin square root of 3. Okay, thus KH1 is Q adjoin square root of 3, and if we flip back up, I think we called that one L2. Way back up here. That's L2. Okay. Likewise, we could do KH2, and that's the set of alpha in K, where sigma 2 of alpha equals alpha. And remember, sigma 2 of square root of 2 is square root of 2. Sigma 2 of square root of 3 is negative square root of 3. And so when we do a similar computation, KH2 is Q adjoin square root of 2, and that's L1. And finally, we have K, fixed field of H3. This is the set of all alpha in K, such that sigma 3 of alpha equals alpha. And remember now, sigma 3 of square root of 2 equals negative square root of 2. Sigma 3 of square root of 3 equals negative square root of 3. And so just by that same kind of computation, I think it's easy to see that KH3 is just going to fix square root of 6. Okay? So those are the three subgroups. So those three subgroups of our Galois group, they fixed the three subfields that we identified just by a quick glance. We found the subgroup that fixed this one, we found the subgroup that fixed this one, we found the subgroups that fixed that one. Okay. All right. One particular corollary, and I think this is actually really, really cool. It says there are only finitely many field extensions F inside L inside K. There's only finitely many field extensions L between F and K, assuming F inside K is Galois. There's only finitely many possible L's. I think that's not obvious. I mean, in our case, we identified three different ones. Q adjoins square root of 2, Q adjoins square root of 3, and Q adjoins square root of 6. But I think it'd be really hard to convince ourselves there's not any other one. How do we really prove that there's no other interesting field extension? That might be kind of a pain. But Galois theory, just because of this bijection, tells us there are, because our group is finite. Proof: ought K over F is finite, so it has finitely many subgroups. All right, that's the end of this lecture. And the next one is going to be an example.